there, you will receive the same nature of the output value. As you know, in SR flip-flop, if it's set and reset, there will be the difference in the input values, that you know very well. So right, in case of SR, if it's set, the S value will be maintained as 0. Then for the case of reset set value, S value will be maintained as 1. Likewise, for the case of maintaining reset, then your R value will be maintained as 1. That's what you might have studied in SR flip-flop. So likewise, if you want to make it as a set and reset state, you need to maintain your J value is in a set condition and K value is in a reset condition. That's what it is. So if you're maintaining your J value as 1, then you would receive the output value as 1. If you're maintaining the K value as 1, you would receive your output value as 0, since that has been located in the portion of reset. Right, so that's what it is. So if you are maintaining both your input value J as well K value as 1, that will act like a T flip-flop. So this is what it is. Any questions so far? JK flip-flop, T flip-flop.
No, ma'am.
Is that clear? JK and T?
Yes, ma'am.
Yes, ma'am.
Okay then. Ma'am has taught you SR and D, right?
Yes, ma'am.
Okay. Then we'll see master slave, right? So next JK we had seen, and T flip-flop. Now the next is master slave. So one of again the circuitry will similar to will look like similar to that of SR flip-flop only. It's similar to SR only. Here S or pins being connected to a NOR latch, right? So here we have NOR and S or has been connected. So again it will going to act as one of your circuit may act as master and other may act as slave. From the master and slave term will suggest one will act in an enable condition, other will go into a idle condition. That's what. If one of your this respective, then this will go for the fact of 0. That is the data you will be providing at this location will become 0. Likewise, if you apply the value at this juncture is 1. So for this case, it will become 0. Likewise, that's why your main calling it as master and it as slave. Also, you could transfer the information at this location as 0, and here it will enable the value as 1. So now this will act as slave and this will act as master. So this is what it is. So one of your circuitry will act as master and other will act as a slave, right? So that's what a master and slave. Every other thing, every other concept is all same only. It's quite similar to that of your SR flip-flop only, right? So here also, instead of applying two input values at this juncture by applying input value, likewise at this juncture, instead of applying two input values at this juncture, we could directly take a clock signal, inverted value at the clock signal, right? So if this acts in a positive edge triggered position, let's consider if this will enable during the positive clock cycle, then what would happen? Obviously, since we have connected across this junction with a NOT gate, purely this will go for the fact of negative pulse. Here it will emerge into a positive pulse, it will go into a negative pulse. So for the negative pulse, it will not conduct, you know very well, since we have connected everything with a positive edge trigger, right? So it will obviously conduct and it will not conduct. So if you apply the value across this, if this clock pulse has become negative, now once it's been started from positive to negative, it starts to negative. So what would happen during this negative transition? Again, it will result in the value of 1. So this 1 value will become, it will start to provide the value across this junction with a positive pulse, right? So here, if it's negative, it will become positive. If this will start to conduct. This is what it happened. So one of this circuitry will, if it's positive, other will become a negative pulse. So the negative pulse will not start to conduct. It will make the entire circuitry lie in a idle condition. From there will not be any possibility of conduction out of this. So at one time only one of the circuitry will conduct, right? So this is why we are mentioning it as master and slave. We could interconnect both the circuitry through a NOT gate, right? So this is how we are getting connected. So whatever the output value we have received out of the master circuitry, that's being connected directly as an input to the slave circuitry. But if that's want to transmitted over this location, this respective location has to be enabled in a positive edge triggered, right? So that's what we are considering. If it's positive edge triggered, then only it will start to receive the information from the master circuitry. From there only it could receive the information. Till then it will not receive any information from them. That clear? Yes.
Yes, ma'am.
Okay then. Now, so also we could write it like, sorry. Okay. Likewise, like this also, so instead of constructing a complex circuitry, like yes, within this flip flop we have circuitry, internal circuitry like this only, but instead of representing that with a complex representation, we could represent with a single flip flop nature. So this is what it is: master flip flop, slave flip flop. We have only a single input we are providing for the master. We are providing the D input. Then that's the output of your master being provided as an input to the slave flip flop. Every other thing and all same, but the clock pulse is being reversed. That is got by making use of NOT gate in the middle of this clock master and slave circuitry. Right, this is how it will look like. Here we have only utilized a single NOT gate. Every other thing and all same. Excess portion we have added is nothing but a single NOT gate. That's it. That's what we have used. Also, we could construct the entire circuitry with the help of what? NOT gate to NAND gate alone. Also, we could construct the entire SOR latch using NOR gate too. That and all you might have studied in SOR flip flop, right? So also you could construct like this. So if you use only one NOT gate, then you could construct this type of thing. Also, if you utilize two NOT gates, then here we have considered a single NOT gate, right? So here at these locations, we have utilized two NOT gates within the master and slave circuitry itself. Along with that, we are using one more NOT to inverse the pulse, that is clock pulses. Also here, but at this juncture, we have considered only a single reduction in the NOT gate. Instead of taking the output value, that is at this location, instead of taking this from Q value and that's getting inverted at this location, we are just directly taking the complement nature of your output value of the master circuit being connected, right? Previously we had taken some NOT gate and output of your master current state, and that's being connected across this junction. This is what we had done in the previous, but instead of taking this respective thing, we could directly take the complement nature of your output value, and that could be provided as an input to the R of the slave, right? So also this could be taken. So by each why we are reducing the circuitry, why we are reducing the gates as well, the components we are using within the circuitry is nothing but in order to preserve the propagation, in order to protect the propagation delay, as well in order to increase the speed up of the propagations, right? So that's what also since we are progressing towards digital, we need to reduce the size of the circuitry as well. The complex nature has to be reduced to a lower extent. That's why we are progressing towards digital, right? So that's why we need to concentrate everywhere, not even the entire circuitry, even a single line. If you can reduce, that has to be implemented immediately in order to protect the propagation delay, right? So that's what it is. Edge triggered. You may know what is edge triggered. Yes, that and all I have put told you here, edge triggered is during this portion. Either this portion, if it's triggered, then that is positive edge triggered. So if that's been triggered across this location, so during this location, if it's triggered, then that is negative edge triggered. Right? So the representation of that would become, if it's positive, it would look like this. If it's negative, it would look like this. So this is how it would look like this. Okay, for this case, here you could observe this. For the case of positive edge triggered and negative edge triggered, the clock pulse will look into a different mode. So the clock pulse will be looked as a different. So here it is been inverted with a negative portion, right? So that's what it is. So this is how the graphical representation will look like. See here, at this juncture, you could observe the negative edge triggered will have a bubble in front of the clock portion, right? So here we have a clock bubble as well. For the case of positive edge triggered, we don't have any bubble shape. Flip flop we had seen. Take also we had seen. Then registers. What's register? What's register? Counter. Are you there?
Yes, ma'am.
Yes. What's register?
Restrict the flow of current, ma'am.
Flow of current. Okay. If you want to store n number of information, since the flip-flop is responsible for storing a single bit information, you know very well the flip-flop is suitable for storing a single bit information. If I want to store n number of information, then what would I go with? Obviously, I would go with a register combination that consists of an arrangement of n number of flip-flops linearly or parallelly or serially or in whatever structure it may look like. But if I constructed arranged n number of flip-flops, that would result in a register structure. Right? So if I want to access the information parallelly, that is if I want to fetch the information in this shape like 1, 1, 1, 1, but then I need to have 4 flip-flops. So each is responsible for storing a single bit information. That are all you know. Yes, a single flip-flop is responsible for storing a single bit information. So likewise, if I want to retrieve the information parallelly, all these 4 bits I need to receive at a time. Then what I have to do is I need to arrange 4 flip-flops linearly. I need to fetch the information from these 4 flip-flops parallelly. At the same time, I have to fetch all the information. So this is how the register will play a role. So let's see. If I want to access a single bit information, every other thing and all same only. Whatever we had seen in the previous arrangements of D flip-flop, T flip-flop, JK, master slave, whatever it is, everything is same. But how we are fetching the information from the flip-flop, that's what we are concentrating in register. Right, so here D flip-flop only we are considering. If I have 0 and 1, I would like to receive a single bit information at the output value. Then, if that's the case, you know very well what the multiplexer will do, which is used to select which type of output value you could you want, what your multiplexer is. So generally, you know very well for the case of you may have 2 input values, but at the output juncture you would receive either of the input only, right? So if this being connected to your input value, you will receive only a single this output value. Let me consider this as 1. So you may receive at this juncture. If this respective output value input value you have received, you may receive the output value as 0. This is what the multiplexer will do. It will just provide a connection between either of the inputs, right? So that's what it is. So if you want a 0 value as an input, then obviously the multiplexer will provide you the connection by making the selection lines, right? So here we would have some select pins. So depends upon the select pins, we will be receiving which type of input value we have, right? So that could be observed out of this. So that's how we are going to fetch the information, right? By making use of the multiplexer in front of the flip-flop you are using, right? So this is what it is. So if your load value has become 0, this load is nothing but it's similar to that of your select pin only. In multiplexers, we would mention this as select pins. So if your select pin is 0, then that would transmit the information input pin value as in, which is in the location of I0, right? So if your input has been represented as I, then if your select pin is 0, then I0 will be transmitted to your output. This is what it is, right? Select pin. So load is similar to that of select only. So in this respective input value will be transmitted to the input of D flip-flop. If your select pin is 1, then obviously this value will be transmitted to your input of your D value. This is what it is, right? So here, if you want to fetch 2-bit, so here we have considered only a single bit information, but I would like to fetch 2-bit parallelly. At the same time, I would like to receive both the bits. Then I'm in need of the arrangement of 2 flip-flops parallelly along with the 2 multiplexers. So for that thing, every other case and all same as that of your first thing I had mentioned. So if this select pin lie in which position, that output will be received. Likewise, here we have some select pins. So that select pin, which if it lies in 0 or 1, depends upon that the multiplexer will provide you the input value. Sorry, output value. That output value will get reflected at the end of the flip-flop. So you will be receiving the output value across the flip-flop. If you want to fetch 2-bit parallelly, the circuitry arrangement will look like this. If you want a 3-bit parallelly, then obviously the same circuitry will also be added at the end of this location. Likewise, it will be processed, right? So here for the case of 3-bit parallel access, yes, same arrangement has been appeared here, but only one condition what you need to do is all flip-flop which should rely on a same clock pulse, clock cycle, right? So if all these been started to emerge at a positive edge trigger, then you need to maintain all has to be in the same position. So if it's positive edge triggered, if it relies on this location, it also has to start to emerge at this location. Likewise, it also has to start at this location. So since all has to be in a synced nature, synchronized clock pulse you have to use, right? All the clock pulses has to be in synchronized. This is a quite important factor you have to concentrate on. If it's 4-bit, then obviously one more arrangement of the flip-flop along with the multiplexer you need to use. All these 4 clock cycles has to be in a synchronized nature. Everything has to emerge at a same clock cycle. So this is what register is, right? So we'll see the shift register in the next session.